The next sum that we see is, so let's just look at the sum first. So they have said, so this is again another operation. As I had mentioned in my first video, you can have any symbols as representatives of binary operations. So here they have taken a up arrow as a binary operation. So they have said, let's call this up because it looks like an up arrow. So let's call it up. So A up B is A minus 1 by B minus 1, and A and B are two rational numbers. So they want us to find out whether A minus 1 by B minus 1 belongs to rational numbers or not, given that A and B are rational numbers. Because again, the first part is covered by the fact that by definition Q is not an empty set. So we move on directly to the second part. So essentially what we do is, so here again, as you can see, this comes from practice. You'll look at the exercise or you look at the sum and you'll be able to find out whether by definition it is a binary operation or not, and you will be able to decide whether you have to prove it or you have to disprove it. So if the question says prove that it is a binary operation, that's easier because you know that you have to prove it, so you take a general form. And if it says disprove it, so again it becomes easy because you know that you need to take an example where the given situation does not work out. But if they just say find whether the operation is a binary operation or not, it becomes a little difficult because then you need to use your intellect to find out whether the operation is actually a binary operation or not and move accordingly. So you have to give an example if it's not a binary operation, and if you need to prove in general if it is a binary operation. So here we have to prove that it is not a binary operation, and as usual I take an example. So I take 2 and 1, both of which are by definition obviously rational numbers, and I take the operation as defined. So it was A up B equals A minus 1 by B minus 1. But if I take 2 as A and 1 as B, then I get 2 minus 1 by 1 minus 1, which is 1 by 0. And definitely any number divided by 0 leads to a chaotic situation where we cannot essentially fathom the value of the number, which essentially means 1 by 0 is undefined. So of course it's not a rational number. So that's an easy way, since the easiest way to find out this example is, since the definition is A minus 1 by B minus 1, and I need to disprove this number to be a rational number for all values of A and B belonging to rational numbers, I can obviously put this denominator into 0. So what I do is I convert this denominator to 0. So obviously B becomes 1. And I can take any other value of A. I can take A equal to 500, I can take A equal to 672, but I need to take B equal to 1. It's sufficient to take B equal to 1 to disprove the fact that this operation is not a binary operation. So this is a comparatively, relatively easy sum. The next, and the final sum for today is A down B is modulus of AB. So we need to find whether this is a binary operation or not. Note that the set that they have taken here is an adjusted set. So what they have said is A and B are the set of all real numbers minus 0. So they have taken all numbers under consideration. It can be a decimal number, it can be a fractional number, it can be a whole number, it can be anything. It can be positive, it can be negative. The only number that cannot be taken under consideration is 0. So that this is how you define sets, where you remove, it's like you have the entire set of real numbers. So that's the number line. This is the set of real numbers, and you just pick out the 0 element and you just drop it off. So you have the entire set of real numbers minus this 0. So you have all the numbers on this side and you have all the numbers on this side. So that is how you define the set under consideration. There is no hard and fast rule that it needs to be a very concrete predefined set. You can create your own set as well. In our future sums, we will probably be defining our sets on our own. So we won't be using predefined sets. We'll create our own sets on which we will be defining our binary operations. So let's look at the final sum. So it says A down B is modulus of AB. Now, if I look at this sum, as I have mentioned before, A and B are two elements which belong to the set of real numbers where 0 does not exist. So by this definition, I can say automatically that A is not 0 and B is not 0, because it's defined on the set where 0 does not exist. And A and B need to belong to the set under consideration in order for the operation to be binary, right? So A and B, obviously by definition of binary operation, or by the definition of the set, are not A and B, are not 0 essentially. Now, If A and B are not 0, that means A multiplied by B is also not 0, which means modulus of A and B is also not 0. And see, A and B are two numbers which are positive or negative, decimal or fraction, real, it's real, rational, irrational, whatever it is, it's a real number other than 0. So if A and B are numbers like that, then AB will also be number like that, because I had mentioned before that a multiplication is a binary operation on the set of rational numbers, and rational number is a subset of real numbers. So your mother asked you to stay in this particular let's say your mother created a border for you to, and she said that you need to remain in this zone that I've created for you. Then your father comes and says, I am redefining your set and I'm saying that you need to stay in this border. So if you follow your mother, it automatically implies that you're following your mother. You're in this bound, which means you're in this bound as well. This small bound, let me just take another color. So let's just a second. Yeah. If I am within this bound, it essentially implies that I am within this bound as well. So if I am saying that multiplication is a binary operation in the set of rational numbers, so rational numbers, let's call this the set of rational numbers and call this the set of real numbers. Rational number is a subset of real numbers, right? So if the multiplicative operation is binary, defined to be binary on the set of rational numbers, it automatically implies that the multiplicative operation is defined to be a binary operation in the set of real numbers as well. So that entire concept of proving whether this form this seeds, if it's a AB modulus, it essentially is an extension of the multiplicative operation. So that portion of the proof where I need to show whether multiplicative operation is binary on the set of rational numbers or not, in this case the set of real numbers other than 0 or not, that essentially wipes out, because I've already said that multiplication is a binary operation on set of rational numbers. If of course if it's your examination, you need to prove that, but here since we are discussing, it doesn't need to be proved. So modulus of AB is essentially belonging to the set of real numbers minus 0. Since I have said that A and B are not 0, it means AB is also not 0. So I can say that modulus of AB is any real number minus 0. So by definition, if A and B are two real numbers other than 0, then A down B, that is what I said, right? Yeah. A down B is also a real number minus 0. So this operation is also a binary operation. So essentially, this is the method, or this is the procedure in which you prove or disprove whether an operation is binary operation or not.